Uh, really wonderful to see so many folks here. Very excited to be here. My first time at Monitorama, but very well aware of the Monitorama community. Had one of my PhD students come and talk last year and just really loved it. So very excited to be here with you all today and share some of the research we've been doing in our group at Stanford. So my name is Peter Bailis. I'm an assistant professor of computer science at Stanford. I study large-scale data analytics. And today I want to talk about next-generation observability for next-generation data, or some of the work we're doing on large-scale data analytics for new types of data, including sensors, video, and various forms of streaming. So this work is sort of couched in the context of a multi-year effort we recently spun up called Dawn, which is kind of collaboration between a bunch of folks, both from sort of machine learning all the way down to systems like myself and Matej Zaharia, who's may know as the co-creator of Spark and Mesos, and then all the way down to hardware architects. And the four of us got together about 2 years ago when Matej and I joined Stanford and asked ourselves, what's a big problem we could go after spanning multiple levels of the abstraction stack that would be a lot bigger combined efforts than if we were to attack this problem solo. And at a high level, stepping back, very easy to pick up, say, Wired, Wall Street Journal, Hacker News, and realize that in some sense it's the golden era of data today, and that we've had huge advances in classically challenging tasks like natural language processing, information retrieval, image recognition, and we're starting to see what I would call sort of societal scale impact of this IT development. So in the form of self-driving cars, personalized medicine. Some of Chris's work has been used to make arrests in human trafficking. And in some sense, there's no end in sight for advances in ML with plenty of data to access. And I think that's really relevant to this community is that if we think about observability and metrics and logs and sensor streams, these are really the food that we feed machine learning models in order to get high performance, high accuracy, high quality predictions. And so in some sense, if we read Wall Street Journal or Wired, our job is done, golden era of data, life is good. But if we look a little bit closer at the story, there's a bit of an asterisk here, in that it really is the golden era of data for the best funded, best trained engineering teams who can afford to assemble very large machine learning pipelines and subsequently productionize these. So to illustrate this problem and this quandary that we see at very large scale across multiple verticals in industry today, I'll draw on one of my favorite papers from the last 2 years, which is Hidden Technical Debt in Machine Learning Systems from our friends at Google. And if you look at this architecture diagram here, there's a huge number of boxes in the diagram, like configuration, data collection, verification, resource management, serving, monitoring, that go into building a production machine learning and machine learning powered data product. But only a small fraction of the real world systems here are composed of machine learning code. So the ML code is actually this little black box here. You can hire a couple statisticians, come with a new loss function. Chances are you don't need one of those. But what you do need is a whole bunch of other infrastructure in order to be successful, in order to take data you have coming into your data centers, in order to apply advanced analytics to produce a model, and then put that model in production and make sure that it's going to be reliable in the event that your data feeds become unreliable. It's going to be reliable as your users and your device populations continue to change. It's going to be reliable as there are all of the normal things we think about in terms of observability and monitoring and SRE, site outages, partial outages, split brain, you name it. So it's like everything we had to worry about before, but times 2. So our goal as researchers, and we're going to go deep into one portion of this, was to ask the question, what if anyone with domain expertise could build their own production quality ML products using data at scale? Without getting a PhD in machine learning or hiring our students in machine learning, without becoming an expert in databases and systems to do that data engineering to wire this together, and to do so cost effectively without understanding the latest hardware. And this is a pretty big, hairy, audacious goal. It also, fortunately, the project timeline coincides with my tenure clock ending, so I have a bit of skin in the game in terms of answering this question. But if we look to history, this has actually sort of happened before. And one of my favorite examples, I think is near and dear to many of our hearts in this community, is search. So search has been around for a long time as a core idea in computing. There's some of the core algorithms for building large-scale indices like we use in systems like Splunk. They've existed since the 1950s. They were developed down the road from Stanford at IBM. And they've been in the literature for a long time. what it really took to make search work well, to get to the point that any developer can kind of add search to an application by linking in Solr or Lucene or using a hosted platform or using a verticalized service like Splunk, was a considerable amount of work around infrastructure and tooling to make these algorithms actually usable and put them to work. To the point where in the search vertical, search is something we all sort of expect, right? Even non-technical users, right? Everyone in my family uses search, even with natural language interface, without understanding what an inverted index looks like. So we want to know, why isn't machine learning the same way? And certainly as a bunch of systems builders, our approach to this is if we're missing big parts of the stack, let's build it. And so specifically in Dawn, we're building out a range of all open source infrastructure, all the way through the different stages of the machine learning lifecycle, all the way from data acquisition, labeling, training, and productionization, but also different levels of the stack, from new interfaces that allow us to specify models easier than ever, all the way down to new hardware that can take advantage of statistical properties of the low-level input. So this is where I come to you today from, which is sort of building up a 5-year effort around open source infrastructure for large-scale data analytics, especially on interesting new data sources. Which brings us to the core technical content of this talk, which I'm going to go very deep on one specific type of data in our efforts here, which I think will be interesting with some lessons we can apply to today's observability data, which is specifically around video. Okay? So why is video interesting for this audience and as a topic of sort of research? Why is it important? Well, what's really interesting about video is that, first of all, it's really rapidly growing. These are 4 clips just pulled up from YouTube. Not much going on in all of them. But this is a road in Brussels. This is an intersection in Taipei. This is a store in Jackson Hole, and another intersection in Wyoming. And there's more and more bits available to us that we can easily capture, store, and transmit sort of all over. And just to throw out some concrete numbers, London alone has 500,000 CCTVs. 300 hours of video are uploaded to YouTube every minute. And these volumes continue to rise because it's just really, really, really cheap to get all of this. So video sensors are like 70 cents for a camera that can essentially capture all of the videos represented here. So we got a lot of data coming. And think about the observability numbers that were quoted yesterday from Twitter. Right? The number of bits coming from just a handful of webcams deployed can easily dwarf that. Now, beyond just the fact that there's a lot of data to think about and to store and process, we can actually do some pretty interesting things about this. We can query this video to understand the world. So if you think about and this is what makes me really excited, okay? If you think about the amount of data that's available in digital form, there's quite a bit about, say, our servers that are deployed today, what users are doing with our sites. But there's not a lot of data about what's actually going on. How many people in this room have their laptops open? What is our individual heart rate? What specific words am I speaking? I guess that's recorded on the live stream. But the hallway track, this is not sort of covered in any digital form. I think video is a really exciting opportunity to start to capture more and more of this, to answer key questions about really the environment that we live in. So we've been spending a lot of time looking at examples of, say, traffic analysis, environmental monitoring, customer behavior, urban dynamics. We can really start to answer questions that previously were just too expensive. Like you'd have to have some grad student sit out in an intersection and count the number of buses going by an intersection. So specifically as a running example, let's talk about counting buses going through intersections. And as a running example, I'll talk about our efforts processing some data in the context of traffic analysis. This is just public data from a webcam in Taipei running sort of on YouTube. And you can go scrape the stream just as we did. So it's increasingly cheap to acquire this data. The resulting question for us as technologists and systems builders is, how do we actually process this, right? How would we actually take this video stream, which is still live, there's not a ton going on, and avoid having to pay someone to sit and watch this frame by frame and say, buses came by at 3 p.m., 4 p.m., 4:01, 4:05, so on. So the really cool thing, which you may have heard of, is these big mathematical models called neural nets that have gotten really good, and they essentially let us query video automatically. So at a high level, from an interface perspective, these object detectors that you can literally download off the internet and just run over whatever data you have, say on your laptop, is to sort of take in visual data like images, so in this case still frames, and using sort of pre-trained models we can get output like the following on the right. We get a bunch of boxes drawn around objects of interest, as well as labels. So here we see a dog, a bicycle, and a car. And what's really exciting about this is that year over year, these neural networks get better and better at accurately seeing, at accurately making predictions and inferences about what's actually in the scene. So the idea here is that you use a lot of parameters, you throw them into sort of a model that you train in something like TensorFlow or PyTorch, and by using so many parameters and nonlinear functions between the parameters, you can kind of learn a good representation. So for example, in our type A feed, we've got on the left the raw pixels, and on the right we've got the output of a model called YOLO V2, and it can detect people. It kind of flickers in and out a little bit, but it does detect this bus. It turns out if you smooth the results of the neural network over time, you get a pretty good picture of what's going on in the scene. And the really cool thing, if you haven't tried this already, there's some really high quality models that are widely available. So you could literally go online and download, it's like 300 megabytes worth of weights. Download the models and apply them to new data. Or you can fine tune them to your particular context. So in theory, we can just download neural networks, run them over video, and answer the question that we had. How many buses passed by this intersection? The problem, and the reason why this is a really interesting CS and systems issue, is that analysis with neural networks doesn't really scale particularly well. So if we take a video like our bus, we actually feed each input, or we feed each frame of the video into the neural network one at a time. So we feed in frame, 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 ask is there a bus, no bus, bus, no bus, bus, no bus, and so on. And the reason why this is the case, and we'll come back to this shortly, is that for much of the training data, or the examples that the neural network learns from, these are hand annotated by humans. So you have a bunch of mechanical Turkers who are looking at images and drawing boxes around stuff, and saying that's a bus, that's a person, that's a dog, so on. And so at runtime, when we turn on the model, it expects the same input it was trained on, which was images. So a video is a sequence of images. Life is good. Conceptually, this is a pretty clean abstraction. The downside is that this is pretty computationally expensive. And sort of my background coming from distributed databases and geo-distributed replication, I get super excited when we talk about scalability. And these things especially don't scale well. So on a state-of-the-art GPU, let's say a $6,000 GPU, I can run a state-of-the-art network around 80 frames per second, right? So if you have 500,000 video feeds, we're looking at over $1 billion in GPUs. Clearly not going to be feasible at scale. And one of the key messages here in this Dawn project is really trying to make this technology accessible to everyone. There are a handful of folks who can pay $1 billion for GPUs. It's a pretty scary group of folks, and we'd really rather make this technology accessible so that everyone can make use of this data and that we can actually do analyses that benefit the world. Like traffic analysis, or I'll show you some bird analysis in a little bit. So the other funny thing that's about this $1 billion figure is that we get really excited because every year there's a new competition for these object detectors. The object detectors get better and better, but as they get better and better, the way they get better and better is more parameters. And so actually the neural networks that won sort of this year's competition, FGFA and MaskRCNN, they're even slower. So on the same hardware, we were getting 80 frames per second. With the latest and greatest models, we're now down to 3 frames per second. Okay, so it's kind of a it's a cool problem, right? You've got this huge amount of data. You've got these really amazing models that can actually start to watch this video and process data for us, but computationally it's just a complete quagmire, right? We're just not going to scale. And so with some colleagues, specifically really smart grad student Daniel Kang and my colleague Matei, we've been building out a new video analytics engine that we call NoScope, which is essentially designed to perform the exact same thing these networks are performing for us currently, which is substantially faster. And what I want to do is walk through some of the insights and the systems intuition we applied to what is a machine learning problem in order to make this stuff actually tractable. So this is kind of about machine learning, but it turned out that a lot of the cool techniques that we're used to in systems, caching and memoization and short-circuit evaluation, these are all things we can apply in ML as well. And with NoScope, we think it's a cool example of why systems thinking is needed for this new class of infrastructure. So to start off, NoScope uses sort of two main techniques to speed up execution. The first of which exploits an opportunity that when we want to understand when buses pass by this intersection, we call that a query here. There's actually quite a bit of redundancy or locality in the input data. So here I have 3 examples of different buses passing by. And below, if you're interested, 4 more stills of individual buses that pass by. And these buses kind of look similar, right? They're different colors, they're in different locations, but they're not like turned upside down, or they're not sort of coming directly at us. They're all going up and down through the street. And so our target objects appear from similar perspectives in video. This is something that we can stare at this video and say, of course, duh, that's really simple. But from a neural network perspective, it's not so simple. Specifically, these neural networks that we take off the shelf, that we download, 400 megabytes worth of weights from GitHub, well, they're trained to detect tens of object categories in arbitrary scenes and from arbitrary angles. So what I've shown here are training images from the training set for this YOLO v2 model that I'll use in this talk, where we're specifically detecting things like toilets and cats and skiers. And we have buses in there as well, because YOLO can detect buses. But the buses are, rear view mirror, looking at a bus from behind. And so if we only want to detect buses in our particular video feed, in some sense we're overpaying, right? If I have a model that's scanning over all the content saying, is there a toilet there? Is there a cat there? Is there a person there? And say, I just want to find the buses, then in some sense it seems like we can get away with something a little cheaper. So the key idea that we adapt in NoScope is what we call model specialization. So we use one of our big, expensive, pre-trained neural networks to generate examples of the object of interest in the video we're looking for. So for example, we could use, come back to our example here, we could use YOLO to highlight these examples of buses in this video feed. But instead of simply running YOLO over all of the video, we could take these examples and essentially specialize or train a very small network to only detect buses in this given scene. So essentially, you can think of this like doing a JIT, right? Based on the query and the data of interest, we can essentially learn a model that only looks for things we care about. And in return, the specialized neural network is going to mimic the large neural network on the video of interest, but it's not going to generalize very well. So if I take a neural network that's specialized at Taipei, I move it over to New York City, it's probably going to perform horribly, right? We'll just miss a bunch of stuff. It'll be poor accuracy and so on. And so we're sort of trading off between generality in terms of the objects we can find and the scenarios in which the model will behave reliably. But we're going to in turn go a lot faster. How much faster? Well, if YOLO v2 takes about 35 billion flops per image, as I mentioned, these are fairly expensive models, we can use specialized models that are on the order of, say, 3 million flops, depending on the complexity of the task we're performing. So it's around 10,000 fewer flops, and on a GPU, this translates to something like 25,000 frames per second. And the reason why there's a bit of a difference here is that you have a lot of work in terms of data loading and decoding and so on. So that's 300 times faster execution on the GPU. Now, other folks have thought about similar problems. I just throw it out really quickly. If you're a neural network weenie, a bunch of people have tried to compress neural networks so they do the exact same thing. It's kind of like lossless compression. What we're really trying to do is do lossy compression. Okay? Just like in JPEG, you lose some of the data, but it looks the same to your eye. What we're trying to do is say, for this given video feed, we're going to train a network that can detect what you're looking for reliably, but anything else you didn't tell us about, well, you got to go back to your big model. Okay. So that's part one. That's opportunity one. That's sort of scene-specific locality. The second opportunity that we looked at in the NoScope project is what we might call temporal locality. So what I've got on the left and right here are 2 videos being run at 30 frames per second of that same Taipei intersection. And you can see this bus is moving on the left, but even during the duration of this 5-second clip, the bus is in the scene and it remains in the scene. Perhaps surprisingly, on the right here is actually also a moving video. And if you look really closely, you can see some of these bikers waiting at the intersection hanging on their bikes. But there's not much going on. And despite the fact that there's not much going on in either of these scenes, because there's 30 frames per second, we're going to do 30 neural network evaluations per second, even in the specialized model case. And so if we can exploit this observation that frames close in time are often redundant, this is 4 consecutive frames, then perhaps unsurprisingly, we should be able to train a fast model to detect this redundancy. And the intuition here is that if you're trying to figure out, is there a person in an image, and I'm showing you image, it may be hard for you to see, is that a person, is that a tennis racket, is that a Shiba Inu? You can probably tell the Shiba Inu, but cute detector just fires, right? But if I ask you, is this the same image as before? Same image. It's very easy to tell if something's the same image. So there's a bunch of literature, like computer vision stuff. People thought it was for years in detecting scene changes. What we essentially do is something really simple. We take a blank frame, shown here in frame 1. We subtract the current frame from it, and if we see something like a ghost bus, it means something's in the scene. And the cool part here, this like the computer vision people say, oh, that's like not super interesting. It's one of the simplest models you can run. But the interesting thing from a systems perspective is that, as I mentioned, when you're asking, did something change? Did something change? Did something change? Did something change? And suddenly you care about runtime. Well, that makes a dramatic difference. So this difference detection, where we subtract frames and then look for differences, can run at 100,000 frames per second on a CPU, right? Which now gives us many, many, many orders of magnitude faster execution time than if we were just doing frame. So if previously, just to recap, we were feeding video in 1 frame at a time into YOLO v2 to get our labels, what we've done in NoScope is essentially build a query plan that's going to combine all of these specialized and cheaper model execution to use the cheapest model possible at each stage. And specifically, we call this a model cascade. It's an old idea in computer vision. The idea is that we're going to use the cheapest model possible for each input. So if the difference detector says nothing changed, we say, whatever the previous label was, that's the label for this frame. If that thing is unsure, it thinks something changed, we pass to a specialized neural network. If the specialized neural network says, nope, definitely no bus, then we say, no bus. If it says, yes, bus, send to the end. If we say, I'm not sure, that could be a bus, it could be a hot dog, then we'll send it to YOLO v2 and we'll keep going, okay? And so the cool part here is that we can essentially, just like a database has a query optimizer, we can essentially optimize both the layout of this cascade and the threshold that decide, are you confident enough to give a result? Or do you need to pass it on to the next guy, okay? So just to put this all together in terms of a typical query, we first sort of run this big neural network over our video to generate training data so we can train the small model. That takes about 75 minutes. We got it down a little bit from here, but you want to get a lot of data so that you can essentially get representative training data. It's also a pain because the big model's slow, and so high quality data takes a while to get, but it's unavoidable because you're going to have to run a big model over your data anyway. We subsequently train our specialized neural networks in our difference detector. These are really tiny, so you can train them in like a couple minutes each, and you can do a state space search over these. We can provide this cascade firing search to figure out when should we short circuit the execution for each. And then finally, after about an hour and a half, we can activate the cascade to process the rest of the video. So kind of to give a sense of what this can do, and the reason why we're so excited about this idea of taking runtime into account in actually performing inference over these large-scale video feeds, I'll show some brief examples of experimental results we had where we ran essentially queries, binary detection queries like bus, no bus, or car, no car, or person, no person, over kind of fixed angle webcam feeds from YouTube. And the interesting thing here is that there's a trade-off between accuracy and speed that we can suddenly expose when we have knobs for determining when to short circuit. So our best result was looking for sort of people entering and exiting an elevator, sort of foot traffic analysis. We can go about 40 times faster at 99.9% accuracy. And if you wanted to sacrifice accuracy even further, this is accuracy relative to the baseline detector. Let's say you're giving 4% accuracy, we can go about 5,000 times faster. Now, in computer vision, you always want to go accuracy, accuracy, accuracy. Like the people just, if you give up a 0.1 accuracy, you suddenly lose the benchmark competition. But in a real world setting, we think that if you can actually get 1,000 fewer GPUs and give up 4% accuracy, that's an interesting trade-off that systems should expose. That's what we've chosen to do in NoScope. And in our worst result, which is this Taipei bus counting example, we're still about 36 times faster at 99.9% accuracy, and then about 200 times faster at that 4% accuracy loss. So just to put this kind of in context and to visualize it, if YOLO v2 executes in 2.53x real time, here we're detecting a hummingbird in front of a hummingbird feeder. This is from the Cornell Ornithology Lab. So you see the bird, it's pretty cool. No scope runs considerably faster, about 2,300 times real time, and really allows you to go from sitting and waiting for your query to complete, for an afternoon or say several weeks if we have large amounts of historical data, to something where we can get a high quality estimate what's going on in just a few minutes. And this one, if you believe Daniel's TensorFlow code, is like something like 94% accuracy for that. Okay. So in the interest of time, I'll probably skip over this, but there's a bunch of stuff in the paper if you want. Not surprisingly, different section and specialization both make a big difference in terms of performance here. We've also been doing work on essentially trying to take these outputs of video processing, instead of outputting just labels, outputting relations, so that we can run, say, SQL over these things. We got a recent submission. I'll just give an example. Someone talked about not inventing a query language yesterday. Like it's a bad idea to invent your own query language. So what we try to do is we try to take the outputs of these video detectors and essentially turn them into SQL-based UDFs. So I can say, select count star from type A, where class equals car, error within 0.1%, and we can compute the number of cars in the type A video feed. Or we can run a query like this, a little fancier, basically find all buses of size at least 10,000 pixels that appear for at least 15 frames in the video. And so with this type of end-to-end pipeline, we can not only run queries over video, we can also combine this with other data sources like, say, pressure sensors, temperature sensors, other event and logging systems. And we think this is a sort of broadly applicable pattern where over time, we'll have more and more sort of UDFs that we can chain and combine and live in sort of SQL, combine this with other heterogeneous data sources. Not only does this avoid a lot of manual overhead, like it's actually a real pain to manually run these types of pipelines, but we can perform new optimizations. And let's give a hint of this since we're running out of time. So if we use a specialized neural network, and we want to get an example, we want to get an estimate of the average number of buses in a scene. Well, we can use the specialized neural network as a cheap filter to select the most interesting events from the video. So in some cases, we'll be able to tell there's absolutely a car there, or there's absolutely one car or two cars in the scene. For something like this on the right, it's kind of tricky to tell, is there one car or two car? But we can essentially use our specialized network as a proxy for how difficult it is to count, and only feed the most difficult images through our big neural network in order to get really high quality results. Just before we wrap up, I think it's really interesting to look back on this work, especially in the context of monitoring time series event analytics, and really think deeply about what these new types of data and the new computational primitives that we have at our disposal mean for application behavioral analysis and increasingly environmental analysis, all the data that's around us that's increasingly collected in digital form. So the increasing data really gives us unprecedented fidelity into complex applications, systems, environments. We really haven't had this much data at our disposal ever before in human history. And coupled with this data availability is computational resources, that is sort of relatively cheap compute substrates, and also increasingly accurate models that we can begin to apply at very large scale of this data in order to put it to work. And so the resulting challenge for all of us, sort of in the systems and infrastructure community, is to figure out how do we make this stuff actually work? How do we make this usable so that it doesn't require, say, a team of data engineers, maybe some machine learning engineers, some data scientists, to actually build out a production scale workflow around this? And we let everyone make use of this in a way that's cost effective. So I think that comes in two different flavors, both of which are critical. The first is interfaces. How do we actually specify these primitives and integrate them with the programming environments that we all know and love, like SQL? Maybe we don't love SQL, but it's certainly better than calling OpenCV. The next thing, though, that's really exciting, at least from a pure infrastructure perspective, is once we have that interface, how do we make it run really fast? These models and these types of computational primitives are more cycle hungry than ever. And so it's going to take folks like us who understand performance optimization, who understand performance engineering, who care about things like runtime and cost. And we can actually begin to optimize these types of workflows. I've gone deep in video because I think it's a really interesting example of next generation data and also makes for a fun talk to watch cars driving by, intersections and so on. But there's really opportunity up and down the stack, and I encourage you to take a look at some of the work we've been doing in open source on our website that essentially tackles a handful of other problems beyond just no scope and video. So we have a system called Macrobase, which is around anomaly detection and automated aggregation to provide explainable analytics on top of event and telemetry and metric data. There's an engine called Weld, which Matej Zaharia has been leading, which basically takes data-driven workflows. Let's say you have a data engineer who's written something up in a mix of, say, Pandas and Spark and scikit-learn. Well, we can actually use compilers to optimize across those different libraries and JIT a hardware-efficient representation for the hardware that's available at runtime. And finally, there's a really cool project called Snorkel, which includes even natural language interfaces to machine learning models, where I can say, explain and express my domain beliefs in a very high-level language, even in, like I said, natural language, and build high-quality classifiers. And there's a bunch of cool applications of this work I'd love to talk about in alerting and generalizing alerting. Why was your alert set at 0.99? Is 0.98 suddenly okay and 0.99 is not okay? Right? We think really a lot as humans about sort of hard constraints. And that's kind of the way that like our brains are wired. But in reality, we like something a little bit more loose. And Snorkel is one example of how we can take precise human specifications and relax them for both higher accuracy and also more robust systems. So in conclusion, I'm a little over time, so I'll wrap up here. Rising data volumes are really requiring entirely new forms of infrastructure for specifying, managing, deploying, and monitoring models. I hope you got a taste of what this looks like in the context of video, and maybe there's some ideas you can take to, say, time series alerting or event-based alerting, especially around anomaly detection and classification here. And the key message to this community is that the systems and abstractions that we've developed for classical problems, whether or not it's containerization, resource management, deploying infrastructure for the last 15 years, will continue to be relevant as we look at this new wave of infrastructure and of data infrastructure. And it's up to us to find the interfaces and the efficient implementations that'll make this type of technology usable for everyone, not just the folks with the billion-dollar clusters, but anyone who has data and has questions they want to answer. Thanks.